So in the previous video we derived a relationship between the microstate and the macrostate of a gas, and we derived an equation for pressure of a gas in terms of its velocity. And the equation that we had was pressure of the gas is equal to 1 upon 3 mn upon v square. Just for the sake of revision, m is the mass of one molecule, n is the total number of molecules in the gas, capital V, this is capital V, stands for volume of the gas, and v square bar, right? This is the mean square velocity, and v square, you know, is equal to v1 square plus v2 square plus vn square by n. So this is the mean square velocity of all the molecules put together. So the pressure of the gas is 1 upon 3 mn upon v square. Now let us say the gas that we are looking at is 1 mole gas. Now if we take for 1 mole of gas, in that case the mass of the gas, the weight of the gas will be equal to the molecular weight, which will be denoted by capital M. Therefore, in this equation, Mn will get replaced by molecular weight, because M is the mass of each one molecule, N is the number of molecules. So this represents total mass of the gas. And when we take 1 mole of gas, the total mass is molecular weight. Therefore, I can write over here M, which is molecular weight. So P will become 1 upon 3 into M upon V square bar, where M represents the molecular weight. Therefore, I can write down PV is equal to 1 upon 3 m v square bar. Now, we also know that PV is equal to RT for 1 mole of gas. This is the equation of state. So comparing these two equations, PV is equal to 1 upon 3 mv square and PV is equal to RT, I can write down 1 upon 3 m v square bar is equal to RT. Therefore, v square bar is equal to 3RT by capital M. And if I take square root of this, square root of v square bar, that will give me square root of 3RT upon M. Now this square root of v square bar, this is the square root of the mean square velocity. And this square root of the mean square velocity, we call it the root mean square velocity. And in short, it is written as RMS velocity. The square root of v square. Of course, I should have a bar over here. Therefore, this is written as VRMS, right? And it's denoted by the symbol VRMS, root mean square velocity. So VRMS is equal to square root of 3RT by M, and therefore VRMS is proportional to square root of T. Right? So this is something which I want to focus on. VRMS is square root of T. So if I try to explain this in word, we say that we can say that the root mean square velocity of the gas is directly proportional to the temperature of the gas. What this means is that the root mean square velocity changes as temperature changes. As temperature increases, VRMS increases. Or we can say that as velocity of the molecules increases, the temperature of the gas increases. And this particular concept, that the velocity of the molecules and the temperature of the gas are interrelated, this is known as the kinetic interpretation of temperature. Meaning that temperature is being connected to velocity, that is kinetic energy. So temperature and kinetic energy are related, and that is why we call this equation, or we understand this concept as the kinetic interpretation of temperature. Also, if I take, say, T is equal to 0, where T is of course the absolute temperature, T is equal to 0, Therefore, Vrms is equal to 0. This Tt is 0, that means this is absolute 0. So at absolute 0, velocity of molecules is equal to 0. That means absolute 0 is that temperature at which all the molecules stop moving. Their velocity becomes equal to 0. And that is how that's how kinetic theory defines absolute 0. It's that temperature at which all molecular motion ceases. So this is the kinetic interpretation of temperature, right? And this is how we are able to connect temperature and Vrms, right? Where velocity is a microstate, whereas temperature is a macrostate. And once again, we are connecting a microstate to a macrostate. And that is the entire purpose of the kinetic theory of gases. It helps us understand the relationship between microstate and macrostate of a gas, right? Thank you.